Have you ever wondered what it takes to build a game like Minecraft? How did its creator came up with such a unique concept and such a fun game to play with? Well, in 2023, one of my main goals was to build one of my first games ever. And to do that, I decided to build a simple clone of Minecraft that runs on the web browser. During this journey, I learned a lot about how Minecraft works, including how the terrain is generated, how trees and caves are placed throughout the world, how the inventory system is managed, and much more. In this video, I'm going to share with you all the concepts that I learned while I was trying to building a very simplistic replica of this game, by also showing you some code. Initially my intent was to build just a simple 2D game using plain JavaScript. But soon I stumbled upon a library called three.js, which is a JavaScript 3D library based on WebGL used for creating stunning 3D content inside the web browser. After having seen some projects built on top of this library, I was quite impressed by the potential that it offered, so I decided to begin studying the core fundamentals of three.js and starting experimenting the library. One day, when I was sifting through the documentation, I stumbled upon an article that recalled my attention. It was named "Making a Voxel Geometry Minecraft-like", written I guess by one of the authors of three.js. It was from that point onwards that my journey to build a Minecraft clone began. Many of you surely know that Minecraft is an open-world sandbox game, made up of a very large number of different cubes, mostly known as blocks. Typically, this type of game genre is often referred as a voxel-based game. The definition of voxel is a bit confusing. Technically, they are 3D volumetric points evenly spaced inside a larger grid. They can be rendered in different ways. Minecraft, for instance, does use cube geometries for rendering this voxel. Each voxel has also some internal data like their x, y, and z coordinates that locate the voxel inside this larger grid. If you put a bunch of these voxels together and add to each of those a specific color or a particular texture, here you have it, a basic representation of a Minecraft terrain. Obviously, it's not that simple. We actually need a way to store these voxels in memory, create their geometries, and then display them on the screen. But one of the major issues to have a world composed of a very high number of voxels is rendering them. Let's see why. Say that we want to render a big chunk of 256 by 256 by 256 number of voxels. We can start by storing each voxel type inside a flat array. The voxel type will be represented by an 8-bit integer, which will give us a range of 256 different types of voxel where we can choose from. Then, iterating over each voxel using a triple nested loop, we create a mesh for each voxel and add it to the main scene. Very straightforward. If we try to run this code, we can immediately see that there are some performance issues. The camera tends to move very slowly, and the scene in general feels very choppy. This is because there are too many objects and geometries to render in a small fraction of time, and the GPU struggles to keep up. In this case, each time we move the camera, we are sending more than 16 million cube geometries to be rendered by the GPU, and if you think about it, this is not even closer to a real Minecraft world, which potentially has a lot more blocks to render at any given time. There are different ways to try to optimize the previous code, like using mesh instancing or merging the geometries, but what we want is something more resilient and dynamic. If we think about it, we can figure out that we are actually trying to render even the voxels that are technically not visible to our camera, and these voxels are a lot. So instead of rendering all the voxels, we can do something more clever. We can just render only the faces of the voxel that are technically visible. This can be visualized in the following geometry. Here you can see how the inner voxels of this geometry are not computed and thus not rendered by the GPU. This technique is called voxel face sculling. Once we know how this technique works, we can also apply a second optimization. Instead of creating a mesh for each voxel, we create a single mesh representing a chunk of voxels, using a custom buffer geometry also known as vertex array object. In the optimized version, we still iterate over each voxel, but now we have to iterate also to each face of the current voxel. If the current voxel face has a visible voxel as neighbor, we do not need to render that face, and we can skip to the next one. Otherwise, we collect the various attributes of the buffer geometry for the current voxel face, things like vertices, normals, UVs, etc., and store them inside the vertex array object. In the end, we will end up having a buffer geometry data containing all the vertices associated to the voxel faces that will form our big chunk of voxel. Updating our previous example to use this two optimization, we end up with this result. You can see that now our camera moves smoothly and without any problems. If we try to move the camera inside this chunk, you can clearly see how there is nothing inside. This is because all the voxel hidden by other voxel has been culled out. So that is basically how voxel-based games render their world. This is particularly visible in Minecraft if you go inside the terrain in spectator mode. As you can see, everything has been culled out, and we can easily spot caves since voxel face composing the cave's walls are exposed to air blocks, which are considered invisible blocks. Pretty cool, right? Let's start talking about how Minecraft generates its worlds. Technically speaking, Minecraft worlds are procedurally generated. That means that the data which represent the world is not baked somewhere in our physical disk, but is generated at runtime by executing some code instruction. Minecraft uses an internal algorithm to generate its unique terrain and landscape, each one with different biomes like forest, desert, mountains, rivers, caves, and so on. In order to generate different worlds each time a new world is created, the algorithm takes into account a randomly generated number called seed that determines the world characteristics. A key concept to understand how world generation works in Minecraft are chunks. A chunk is a piece of world 16 by 16 block wide with an height of 384 blocks. A Minecraft world is divided into several of these chunks, which are adjacent to each other. Chunks are an essential part of the world generation, because they can be dynamically loaded and unloaded while the player moves throughout the world. This not only resolves the problem of initially generate the entire world in one shot, which will be practically impossible given the size of the world, but is also permit to get ease on the memory usage since the chunks are unloaded when the player gets out of a certain range. So, as you might have guessed, Minecraft does generate only the chunks near the player by a certain radius. This radius is mainly controlled by the rendering distance that you have set on your game settings. A very important property of chunks is that they can be reproducible under the same seed. That means that even if a chunk is unloaded off from the memory, when it comes to be reloaded again, it will be exactly the same as the previous one. This is a very critical part, since we want our world to remain the same when we go back to areas of the world that we have already explored. Now that we have a basic understanding of chunks, let's see a simple diagrams to understand how I structure my code to simulate the terrain generation. So we have a root class called terrain that basically represents the terrain as an entity of our game scene. Since it's an entity class, it will be updated every frame by executing the update method. The thing to notice here is that the update method needs the player position in order to generate the terrain accordingly. The terrain class is composed by two subclasses, named terrain loader and chunk manager. The terrain loader basically is in charge of loading and unloading the chunks based on the current terrain origin, which corresponds to the current player position. To do this, it does use the chunk manager class. As you can see, this class keeps track of the currently loaded chunks, the chunks near the player, and it does offer an API used by the terrain loader to load and unload or even update a chunk based on a particular position or a chunk ID. If we dive into more details of the chunk manager class, we can see that it offloads some of its works to a worker pool for generating the chunks. This is because generating a single chunk requires a bit of effort from the CPU, and thus it cannot be executed on the main thread, otherwise the game will be unplayable. Each worker does use another class named Chunk Geometry Builder, which is in charge of generating the buffer data geometry for a single chunk, using all the optimization that we have seen before. So the Chunk Geometry Builder generates all the chunk geometry data, like vertices, normals, colors, UV coordinates, in order to be sent to the GPU later on. Once a worker has finished generating a chunk, it returns back to the chunk manager the geometry data for the generated chunk. This data will then be forwarded to the chunk mesh manager that will be in charge of generating the mesh for that chunk and add it to the game scene. So here we have it, our basic dynamic terrain generation. Let's see it in action. As you can see, the terrain gets updated accordingly to my current position. Behind the scene, Minecraft terrain generation uses what is known as Perlin noise. Perlin noise is an algorithm which generates a random pattern of values that appear to be random but have a smooth and continuous transition between them. This noise is used to create a natural looking terrain that is not completely uniform but still feels coherent and organic. One of the main usages of Perlin noise is to generate the height and the shape of the terrain. You can think the terrain being represented by a 2D map where each point in this map represents the terrain height in a specific location in the world. Higher value means higher terrain and vice versa. If we then smoothen out these values, here we get our fancy hills and valleys. But Minecraft does more than that. It actually combines several of those Perlin noise based maps to output the final terrain shape. I could continue going on into much more detail about terrain noise generation, but for this video I will stop here. In case you want to get a deeper understanding of this subject, I suggest you two great videos. One of Eric Nyberg called Minecraft Terrain in a Nutshell and How Minecraft Works by Alan Zucconi. Okay, now let's see some diagrams to understand how do I put these things together to generate the terrain shape. I started out by defining a root class named AbstractMap. This class contains the word seed and a prng function. The prng stands for Seeded Pseudo Random Number Generator, used for producing sequences of random number. The core property of this function is that it is deterministic, so under the same seed and the same execution order, it will produce exactly the same numbers. The class local to the map has the responsibility to store the data for each x and z location of the world inside an hashmap data structure. This hashmap can be seen as a cache, since every time we carry for a specific point location, we store the value inside the map so that the next time we do the same query, we don't need to recalculate the value again. The noise2d-map class defines a simplex 2d noise function, which responsibility is to generate a noise value for a specific x and z location. Once a value has been generated for a specific location, it will be consequently stored inside the cache provided by the local 2D map, which this class inherits from. We have then a set of different noise2d maps, each of which has a specific purpose. For example, the continental map calculates the terrain base height for a specific location, the erosion map tells us how much the terrain is flat or rough, or even the PV map, which tells us if the terrain in a specific location is more mountainous or hilly with high peaks, or if it is more flat or low-lying with low valleys. These maps combined together form the height map, which returns the terrain height given a specific x and z world coordinates. Now let's see how do we effectively use these maps to generate our terrain. So far we know that a Minecraft world is composed by a set of chunks adjacent to each other, where each chunk is just a set of blocks, or better voxel, placed seamlessly. What we actually are missing is what block to place into a specific x, y and z location. How do we decide what type of block to put into a specific point of our world? We have a very large set of blocks to choose from, like grass blocks, stone, water, sand, dirt, and you name it. So in order to resolve this essential question, what we do is basically loop over each block inside a chunk and then perform some kind of magic to decide what block to place there. Here, what we are doing is looping over each block of the chunk and then executing the method generateBlock provided by the class blockGenerator, which will return the block to place. So nothing crazy here, let's dive into more detail. The blockGenerator class is an abstract class, so what now I'm showing you is a concrete implementation of the blockGenerator named TerrainGenerator. This class is in charge of generating the blocks under the surface level. Inside the generateBlock method, we can see that we first get the current surface height level from a terrain map. If the current block y coordinate is above the current surface y level, we place the hair block, or just an invisible block. Otherwise, we take in consideration what level of depth we are currently in inside the terrain. To make things more clear, let's take a look at what blocks we do generate at level depth surface. Here, what we do is basically evaluating what type of biome we are currently in to decide what block to place. For example, if we are above the snow level and the continental type is far inland, we place a snow block, whereas if we are in a lower level terrain like coast or ocean, we put sand. This obviously is an oversimplistic approach to just simulate biomes. In real Minecraft, the algorithm to select the correct biome is way more complex, but the core principle remains the same. Let's see also another type of block generator named features generator, which is responsible for generating the blocks related to terrain features like water, trees, clouds, and so on. The approach is the same as the terrain generator. We have access to some maps, in this case the terrain map and also the tree map, another special kind of map, and then we evaluate the current surface level. If the block is below the surface, it's not the responsibility of this class to generate a proper block, since the features can only spawn above the surface. If we can spawn some sort of terrain features, we perform some checks to see what kind of block feature we can place there. It can be a tree trunk or a trunk leaf, or maybe if we are near the cloud level, we can place a cloud block. You get the idea. So this is basically how did I choose to implement the terrain decoration phase, and this is what the final result looks like. Here we are getting from a mid area into a coast area, and we can see how sand and water start spawning at the surface level. Here instead we are approaching a snowy mountainous area, and we start getting grass covered by snow. Pretty cool, right? The next big thing I want to talk about is the actual gameplay. Elements like player physics, or even the possibility to editing the terrain by placing or removing blocks and saving our progress. Let's start by taking a look at how did I implement the player entity which can move and interact with our fancy world. Many 3D games tend to represent the player entity as a perspective camera which can be controlled by our keyboard and mouse. This camera can be thought as being placed at player eye level, so it's basically simulating the view of our player. Obviously, aside from moving this camera, we need also to simulate a rigid body moving throughout the world. This means detecting the player collisions with the terrain and applying proper physical response like sliding against the walls or avoiding falling through the terrain. In order to do this, our player, along with his camera, has an invisible bounding box which represents our player rigid body. This box makes easy to detect collisions with the world by applying some collision detection algorithm like axis-aligned bounding box. Since I don't want to dive into too much detail on how physics works on a 3D game, as it is a very broad topic and honestly I'm also quite a beginner in this field, I will quickly show you the player's update method. As you can see, the player entity is divided into several inner components, such as the player physics, the player collider, the player controls, etc. Updating the player just means updating his inner components, such as the physics, which include collision detection and response, its collider mesh, and finally the editing controls, such as placing or removing blocks. The two most interesting parts are the physics and the editing controls. So let's take a look at how physics works first. Implementing player physics and especially collision detection and response was one of the most difficult tasks of the entire game. In addition to a deeper understanding of linear algebra, including vectors, one must be very familiar with some laws that model the player motion, including the famous kinematic equations. But leaving that aside, let's see what I came up with. So basically I first update the physics mode and the ground state of our player. Physics mode stands for the type of controls currently active. It can be of type simulation controls or fly controls, which is very similar to spectator mode in Minecraft. Ground state instead tell us what state the player currently is, like walking, jumping, falling, running, etc. After that, we update the player velocity, accordingly to the keyboard keys pressed. Before updating the player position, we need to detect whether the player has collided with some blocks, and if it is, apply some sort of collision response like freezing or sliding the player against walls. Only after having applied a proper collision response, we can update the final player position. Finally, we apply things like gravity and friction to our current player velocity, which will give us the effect of controlling a real body in motion. Basic stuff. Next up is player editing controls. This basically means detecting whether the player has placed or removed a block in the current frame, and update the terrain accordingly. Here we respond to the player having pressed the left mouse button, which means that it wants to remove the aimed block. So what we do is first get in the target block aimed by the player crosshair, and then remove it from the chunk which the block belongs to. Then, if we effectively have removed a block, we play a sound effect, and also update the inventory by updating the total amount of the erased block as simulating the player picking up the dropped block. Same story if the player instead has pressed the right mouse button, so it wants to place the selected block. We first detect the position where we can put the block. We effectively place the block by updating the target chunk, play the proper sound effect, and finally decrement the total amount of the selected block. Now a little extra. I want to show you up how do I detect the target block aimed by the player crosshair. The idea is to basically cast a ray from the current player camera up to a very distant position equals to the camera z-far plane value. Into code, this will look to something like this. First, we get the normalized screen coordinates of our crosshair position. From there, we construct the ray and then execute a very sophisticated algorithm to detect if the ray has intersected some voxel while casting this ray. If it has intersected at least one voxel, we return the first voxel intersected. And this is the final result of the editing controls implementation. We can place different blocks or just remove the aimed ones. Here, for example, I'm constructing a very simple house just for testing this out. Another important feature that my game couldn't miss was saving game progress. That means implementing a system that permits the user to save his progress in order to be resumed later on. To save the game data, I decided to use the IndexedDB, which is a very powerful database that is already built into most modern browsers. The IndexedDB permits to store almost any kind of values by keys, supports key range queries, and most important, can store much bigger volumes of data than the local storage. Saving progress basically means saving all the data that can be regenerated automatically from our code. This includes several parts of our game such as the word seed, the player inventory, the player position, and also the direction where the player was looking at before he saved and exit the game. Speech apart has to be done instead for the terrain editing changes. Obviously all the terrain changes must still be saved into the IndexedDB, but the process of saving this type of data is a little bit different. Since our terrain is dynamically loaded and unloaded as the player moves around, we have to save our terrain chunks changes every time a chunk is unloaded from memory. So what I have done to implement this behavior is every time a chunk is modified, it is marked as dirty. In this way, when the chunk is getting unloaded and it is marked as dirty, we first save its geometry data into the IndexedDB, and only then we proceed to unload the chunk from memory. When it comes to reload the same chunk in memory, we first check if it is stored inside the IndexedDB by looking up the chunk by its chunk ID, and if it is stored, we load it from there. Otherwise, we simply do regenerate the chunk automatically using the word seed. A little bit tricky, but it does the job pretty well. So that was pretty much it for this video. As you might have seen, I've barely scratched the surface of some of the major topics that cover the fundamentals of such a simple but very complex game like Minecraft. Actually, I even left out some parts that I would like to talk about, like the inventory system or the caves generation, but I think this will be appropriate for separate videos, since they were quite a large task to implement. So let me know if you would like other follow-up video where I could go into much more details of some area of this game, like the terrain generation or the physics engine, or some elements related to the core engine of the game. Of course, if you want to try the game, you can find the link down in the description, along with the link to the GitHub project, which is completely open source and open to external contributions. Before ending up, I want to give some credits to some authors which made these videos possible. Starting from the author of the article Making a Voxel Geometry, which was my starting point for this project, up to other content creators like Eric Nyberg and Alan Zucconi, which made 2 useful videos that helps me out understanding how Minecraft terrain generation works behind the scene. And also shout out to Games with Gabe and Simon Dev channels, which, as well as having several videos for understanding the core principle of game development, they itself documented their journey building their own Minecraft replica. So be sure to check out these channels and leave it some support. With that being said, we will see in the next video.